All right, let's get started. Today, we're putting on our Chief Systems Engineer hats. Our mission? To lay out the complete engineering blueprint for a next-generation micro-EV battery. We're going to break down how you design a system that's not just cheap, but also smart, incredibly safe, and ready to compete on a global scale.
And this quote, it just nails it. For years, the only thing that mattered was cost, cost, cost. Well, that era is over. Done. Today, it's a high-stakes balancing act. You've got radical affordability on one side and this complex web of international regulations on the other. The game has totally changed, and if you want to win, you need a brand new playbook.
Okay, so let's really dig in here. First up, we need to define our core mission. What is the exact problem that we, as engineers, are being asked to solve in this new environment?
And this slide lays it out perfectly. We are moving away from pure cost minimization, which is really just a race to the bottom, and we're moving towards what the industry is now calling compliant affordability. See, it's not about being the cheapest anymore. It's about being the smartest with your money while making sure you can meet the toughest safety and data regulations anywhere on the planet.
And here it is, the number that keeps engineers like us up at night. Under $100 per kilowatt hour for the entire pack. That's the cells, the casing, the electronics, everything. And hitting that number while juggling all these new global standards, that is, without a doubt, one of the toughest challenges in automotive engineering today.
So, next up, we have to talk about that regulatory minefield. In this section, we're going to define the non-negotiable rules of the game, the things that shape our design before we even draw the first line.
You know, what's fascinating here is how every major market is pulling the design in a totally different direction. China is absolutely laser-focused on fire safety. The EU? They demand complete data transparency. The US is all about physical crash integrity. And then Japan wants the battery to actually be part of the car's crash structure. The challenge is, you have to solve for all of these at the same time.
I really want to zoom in on China's rule for a second, because this isn't just an update, it's a complete revolution. The old way of thinking was about giving you, say, 5 minutes to get out of a burning car. The new standard is about preventing that fire from ever really starting. This single requirement to block thermal runaway changes everything about the design. It basically takes certain chemistries like high-nickel NCM right off the table for these low-cost cars. They're just too risky now.
Then you've got the EU. Their battery passport has nothing to do with physical safety. It's all about data integrity. Starting in 2027, every single battery needs a digital birth certificate. You can scan it with a QR code, and it tracks its entire life. So what this means for us as engineers is that our battery management system, our BMS, it has to be built from the ground up to be a secure data vault. It's a day one requirement.
Okay, so we've got the rules of the game. Now, let's see how the competition is tried to play. In this next section, we're going to take apart what the leaders are doing, not to copy them, but to learn from their smart moves and, just as importantly, from their strategic dead ends.
First up, the king of volume, the Wuling Hongguang Mini. The absolute genius here isn't something flashy. It's their choice of voltage. By keeping the system in that 96 to 115 volt range, they get to skip all the expensive high-voltage rated power electronics. It's just a brilliant engineering trade-off that slashes the cost without really hurting the car's main purpose, which is driving around a city.
And on the other end of the spectrum, you've got the Citroën ME. Now this one is clever. It uses a 48-volt system so it can be classified as a quadricycle in Europe, which lets it dodge a whole bunch of tough high-voltage rules. But here's the catch. It's a strategic trap. The low voltage means performance is limited, and, critically, there is no way to add fast charging, which is what the market wants now. It's a solution for a market that, honestly, doesn't really exist anymore.
And that brings us to the Geely Panda Mini. This is the car that proves the market is growing up. It offers 22 kilowatt DC fast charging. You know, this isn't some luxury feature anymore. It's quickly becoming a basic expectation from customers. Just getting from A to B isn't good enough now.
So what's the big takeaway here? Is that the market has moved on. The question we have to answer isn't just how do we make it cheap anymore. Now it's how do we deliver the fast charging and the performance that customers expect while staying under our cost target and meeting that global wall of regulations. That's the real challenge. All right, that brings us to the core of our mission here in Section 4. Based on all that, the regulations, the competition, we are now going to forge our engineering blueprint. These are the big, data-backed decisions that will define our entire system.
Okay, the very first and maybe the most critical decision we have to make is about the chemistry. It really boils down to two main contenders right now. On one hand, you have LFP, Lithium Iron Phosphate. It's the proven, low-cost workhorse, but it really struggles in the cold. On the other hand, you have sodium ion. This is the Challenger. It's got fantastic cold weather performance, could be even cheaper, but its energy density isn't quite there yet.
So when you lay out the data like this, the trade-offs become crystal clear, right? LFP gives you more range for the same amount of weight, but sodium ion, well, it's the obvious winner for cold places like Northern Europe or Canada. Plus, it gives us a really important hedge if lithium prices go crazy again. And on safety, they're both incredibly safe and they both easily meet those tough new thermal rules.
So what do we do? Which one do we pick? Well, the answer is, we don't. The winning move here is to engineer a flexible platform. We're going to design a single battery pack architecture and a single BMS that can accept either LFP or sodium-ion cells. This lets us perfectly tailor the car to a specific market without having to re-engineer the whole thing from scratch.
Now, how do we solve that no thermal propagation rule without blowing our budget on expensive liquid cooling? We do it with a really clever 3-layer passive system. First, the aluminum case itself is designed to act like a giant heatsink. Second, we sandwich these ultra-thin aerogel firewalls between the cells to stop heat from spreading. And third, our BMS acts like a smart guardian, constantly watching the temperature and automatically slowing down the charge if things get a little too hot.
All right, let's put all the pieces together. This final section is our winning strategy. This is how we take all these engineering decisions and turn them into a competitive advantage that's going to last for the rest of the decade.
Here's our 3-part play. First, platform design. We use a cell-to-pack approach with modern short-blade cells. This gets rid of unnecessary parts and lets us pack in more energy. Second, that chemistry-agnostic BMS we talked about. It future-proofs our design. And third, we build the EU battery passport functionality right into the BMS from day one. We're not just ticking a compliance box, we're building a key that unlocks the entire European market from the moment we launch.
And that, right there, is the new reality. In today's micro-EV, the battery is no longer just some component you buy. It is the central strategic asset of the entire vehicle. And its success depends on this perfect blend of smart engineering, regulatory foresight, and supply chain strategy. This is how we're going to win.